whiteboard. You got no, because I didn't figure out what I want to share. So I'll put them up afterwards, but I'm still trying to figure out what I want.
Well, don't forget we have trivia. I can't drive that fast. I park over here.
Yeah.
Just like, get out easier. It's great.
So it's either no lunch or skip trivia. At least the start.
Yeah. Which is like the whole
I
setup.
have a GUI I can share that you can look at home. So we'll let you play with some data, adding points, subtracting points, and it will search for them. So the question was whether I'm going to do an example with a support vector machine. And I have a GUI which I've written, which will let you add points and subtract points, and you can then say search and find. So I put this onto Canvas. Maybe I'll make a homework problem for it, but it's mostly just go and play with it, and you'll see that. I do have the next homework in mind, and so I'll get that posted this weekend. The next homework is an introduction to neural networks. It's a little bit of coding, which is the beginning coding you need for your project 3. The project 3 is on neural networks. And what I've observed in the past is where students get stuck in their programming. So I'm going to break off part of it as part of a homework, similar to how I had you code to read the data and do the RMS before you code the project, which got you up and going. You're able to read the data. You can't read the data, you can't do the project. So here we have you do a small part on homework 3. So we're moving today into neural networks. That's usually something that students get excited about. You hear a lot of hype, and a lot of it is hype.
Perfect.
Okay, I've been around long enough that I'm a little bit of a skeptical about hype. Okay, and I'll show you why when we get a little bit further through things. Okay, neural networks can do many good things, so I'm not debating that, but there's still some of it's a lot of hype. This is covered in your textbook, chapters 5 and 6. So that's where you should be spending your time this weekend studying to read. I will get the Canvas updated. I'll add parts of these slides later today, and I'll add other stuff in on Canvas for neural networks. And if I don't, remind me, okay? Because I get distracted. So last class, or a couple classes ago, we talked about linear discriminants, and you had that concept. And we talked about how linear discriminants wind up with a discriminant function similar to what you have for Bayes, which can be written as a weight transpose times your data plus a constant. So all that math up above, you're all experts at, nod your head. And it all winds up down here where we have a discriminant function taking your weights, multiplying them by your data, your feature vector, and adding a constant. And if it's positive, you make one decision. If it's negative, you make another decision. And we talked about how we could write those weights in this diagrammatic format, where you take your weight 1 times your first feature element, weight 2 times your second feature element. If we had more than 2 features, like 8 of them, like in your project, this would be x1, x2, x3 down to x8, m00, mu02, mu11, etc. Each one multiplied by a weight, add it all up, and compare it with 0, the comparator. You saw this last week. Now that idea is something mathematically is not new, but it's now been framed in these things called neural networks. So I'm going to kind of show you where the thoughts for neural network came, where all this other stuff, where it converged, and then where it's gone and where we get to today with all of the deep learning. Did you hear that? So neural networks are based on physiological models of neurons, with things in your brain that sometimes work. Okay, it's a very parallel structure. It's not an algorithmic thing. It's not like hey nearest neighbors where you say do this because. It's not like Bayes where you say the probability is here, do this because here's your algorithm. A lot of it is, it works. Which is good. If it works, it's good to have things that work. However, there's also a lot of critical infrastructure where we don't want to just rely on, well, so far it's worked. So I assume it's going to work tomorrow. Critical things like that, you don't want to rely on like that. So a lot of it is a very black box strategy. And I need you very much so coming out of this course knowing that it's a black box strategy as compared to these other algorithms. You can see mathematically why KNN works, why Bayes works, why SVMs work, hopefully. And I'm not saying that neural networks are totally bad. They do work. But you need to understand and you need to have a little bit of realistic, well, okay, this is hype, this is reality. Don't get caught up in the hype. They are definitely tools. I do use them. But don't get lost in the hype. Be realistic about what they're capable of, what they're not capable of, and be good engineers. And we're hoping that if we give them a lot of information, a priori information, what do we know about the problem? And we're going to hope that with a little bit of training, that they're going to behave like we want them to. And then this comes into where you need to take all that you've been learning in the first two projects, and I'll show you later how you want to apply that knowledge you've gained. You have all gained knowledge. I can see it. Even if you're struggling with a project, I can see you've gained knowledge. And I'll show you how to use that to understand what you're getting here. So there's connections of elements, units, things we call nodes and neurons, and information is stored by weights on each node. So that's just like this stuff here. Neurons, different pieces, weights, there are connections in between. It's mathematically the same things you've seen before, almost. It can work on a high dimensional feature space with lots of complex interactions between variables. These network patterns got really, really complicated. I'm going to quickly flash about 20 different slides later. It can get really complicated. Or it can be really simple. Usually it's complicated. We try to work through there. And then there's lots of options for how we connect the pieces. Like if I gave you a big set of Legos and put it together, how many ways can you put them together? Lots and lots of options. Okay. Now, nowadays, kids buy Legos in a kit and they're told exactly how to put them together. But think back to the fact that if I just gave you a bag of Legos, there's lots of ways of putting them together. And we can do neural networks in both hardware and software. And this is an important thing. Is that it's really easy to do them in both hardware and software. Well, really easy is kind of in quotes. But that allows you to implement them in hardware, which allows you to then get acceleration. We don't need to do everything in software. The software runs on hardware, something people seem to slightly forget. But it can be done and implemented directly in hardware. So history. I think it's really important that you understand where they came from. You don't have to have all the names and dates memorized. I'm not going to test you on that. But I want you to realize that these things were not just developed yesterday. 1943. You're back when your parents were young, grandparents were young, depending how old you are. Okay, long ago. McCulloch Pitts said, this is how I think those brains work. Because they recognized that animals were intelligent. And there was desire to figure out why are we intelligent. We still want to know. There's still a lot of research out there. And they were able to hypothesize and simulate building circuits. Putting some things together in there. And so they came up with some general ideas of what they thought. And you've probably seen this model in your biology classes, that there's a nucleus, the center of your brain cell, and all these little dendrites coming out. And some of the stuff are receiving input from neighboring neurons. And then they're sending stuff out to other neurons. So the dendrites are the input, and the arrows are the synapses coming out. And it comes into another one and comes out. We put all those pieces together. And if we put a whole bunch of them together, somehow it works. Okay. Now, taking the 1943 simplified view, we put a whole bunch of data in. We scale them by weights. We add them all together. All the stuff coming in comes into one cell. And then, if we get enough coming in, we fire. Something comes out. Now, originally what came out was a 0 or 1. There's lots of options there. Something is coming out, depending on what's coming in. Very simplified. Part of it is simplified because it's 1943. They didn't have MRIs and they didn't have all these other things there back then. But they were just starting to figure out what did they think was working. And they said, well, we think this is what's going on, taking little mice apart. This is how we think the brain is working. Then in 1949, Donald Hebb did some more work. He became very famous for saying that he thinks that the more you use them, the more they fire, the more they learn. And you hear this in our everyday speech. We talk about, exercise those neurons. The more you do, the more that they're going to learn and whatever. You hear this, we talk about this. Whether it's exactly how it works or not is irrelevant. We talk about it in a non-technical sense. You're working on stuff. Is your brain firing? We talk about that. Keep doing more problems. You're going to get it stronger. Strengthen those synapses. We talk about that. And that's based on what Donald Hebb in 1949 said. All that stuff we say today. And these people, in many ways, are more biologists than they are engineers. But they were also engineers trying to say, can we take the biology and use that to build technology, to build computers, to build circuits? And remember, what did the computers look like in 1943? Buildings, vacuum tubes, manual switches, plugging things in. Did any of you see the movie about in England, the code breaker? Imitation game. They're literally plugging things in and setting things. So they're taking these ideas, not with a modern computer, not with a very ultra modern computer. We're not even talking the computers that sent the man to the moon. We're talking 1940s, these things with plugging things in. and lots of mechanical switches. But even with that, they're still trying to say, what can we do? Okay. So just kind of keep perspective there. Okay, well, people kept working. The next important guy on the scene was Frank Rosenblatt. And he really did a little bit more work on that. And I'm going to pause this slideshow and show a slideshow my doctoral advisor put together. Where is it? Because my doctoral advisor, George Nagy, did his PhD under Frank Rosenblatt at Cornell in the early 60s. So I hear lots of stories from him. And he put some of them, they had a Frank Rosenblatt anniversary conference back in 2011. And he and I still get along and still keep in touch. So I got his slides from that. So this is not me talking, this is George Nagy, Dr. George Nagy talking. And so Frank Rosenblatt is a person. Abstract, you don't need to read that. Lots of things about him. He studied at Cornell and became a researcher. And he's a researcher really in neurobiology. Trying to see how those biological neurons work for learning and what can be done to take that into engineering. Really early biomedical engineering. And he liked to do non-work things too. He had a number of papers. But there's his really significant paper, The Design of an Intelligent Automaton. Now you've seen it. This is where he's introducing the concept of a perceptron, which even today is the building block of modern neural networks. Okay. So his philosophy was that these perceptrons were really great things. They're economical, relatively few units. Again, remember what they had for computers. They were starting to get up someplace between the imitation game and the moonshot. Computers are growing. There's someplace in between those two levels, but they're still huge. There's still lots of discrete components and working the way into there. So if you put these neurons together, these perceptrons together, they can be robust to failure. If you're partying too much on Saturday night, you can still wake up on Monday and get on with life most of the time. Don't drink too much on Saturday. And they don't just memorize the input. There's a feeling of learning, which is different than memorizing. And think about that as to how that applies to you in your schooling. If you just memorize things, you tend not to do really well. You can do well in some of the earlier stuff. In biology classes have a lot of memorization. But for all you're doing in your degree program here in engineering, memorization doesn't cut it. You have to really learn and understand it and be able to apply it to something new. So these models, he was aiming to not just memorize the input. And he's saying that they don't want them to violate what they, at the time, 1958, knew about the central nervous system. And he wanted them to be able of spontaneously organizing and representing their environment. And the environment is not the whole world around you. The environment was whatever was given to them. They're in a box, whatever was given to them. So this is what Frank Rosenblatt was using in his mindset as he was developing his first neural network. Some stuff from the book that he wrote, some stuff in there, calculations of Frank's. And then he was aiming to see how the physical world was able to sense the biological systems. He was looking to see how information was stored and retrieved, and how what's already been added there influences what you do in the future. Okay. And so he created this category of neural networks, which are really just building block elements called perceptrons. And he considered them being put together into a brain. How to get that out? No, I'll try that before. It won't go away. So it's not there when you want it, and it's there when you don't want it. So he's aiming and saying that these biologically plausible, and plausible is an important part here, plausible models, they do not perfectly match biology. He knew this, he was okay with this. But they are inspired from it. Again, think of like an airplane. What inspired manned aviation? Birds. Do airplanes fly like birds? No, but they work. So they're inspired, they're built on them. They have some of the aerodynamics from the wings. They take pieces here and there, but they don't do everything. Okay. So they're biologically plausible. They can kind of fit in there. There's things you can see, but we're really trying to mimic things, using that as inspiration, not as a perfect model. So the people who are influencing him, number of people, McCulloch and Pitts, I showed you them, 1943, were really big influencers. Heb, I mentioned, was a really big influencer. Lots of people who influenced him. He did not come along and think about it totally in isolation. There's a lot of other people out there who did things. Here's one of his diagrams, early diagrams. The nervous system, how he outlined it, how he titled it. Having the environment, feeding in, and then in and back out, sensory tracts, central control network, everything coming out, muscles. That's how he just very, very broadly described the nervous system. And then he said that he thought that these things feeding from layer to layer influence and organize what's going on in your brain. We talk about there being various nerves for your eyes, which feed certain parts of your brain, which feed other parts of your brain. These concepts, again, they were new then, but taking these concepts which still apply and saying, how can we use this in computer science, in engineering, in mathematics to represent what's going on in that brain? Because they knew the brains were smart. Beginning of the class, they're talking about putting a 3-year-old in the box. Okay, so there's something going on there which we want to try and duplicate. You're going to take your input and feed the input through your network, and then from your network values to an output. It's very discrete, defined output. So he was a builder, and he physically built a computer called the Mark I perceptron. My doctor advisor helped me some work on this. Okay, and it was built to do a very simple, trivial problem. Remember sensors then? CCDs didn't exist. Okay, so they had the input recognizing letters of the alphabet, even lower resolution than what you guys are doing. Okay, very, very simple. It's not commercial OCR. It was a demonstration of can we build something that's able to do learning and character recognition historically has driven a lot of advances in machine learning. Deep learning was invented because of character recognition. It was not invented from some other topic. It came out of the character recognition community. From a doctoral student who the professor said, well, I don't have time for you, go try something else. And so he did. Always listen for advice. So it's not making commercial OCR, but it was able to recognize some isolated letters. Okay. And the point was that it was not pre-programmed how to do it. It was shown the letters, it changed its weight values, and adjusted to recognize the letter
Optical character recognition.
by being zapped when it made a mistake. No animal
It would be
cruelty.
a good question. I highly doubt you'd be able to.
Let's try. Yes.
What's OCR stand for?
Optical character recognition. So think of the perceptron as a brain model, and it was not an invention for pattern recognition. But the thoughts were that brains were really intelligent, able to recognize patterns, and can we then therefore use it? And that perceptron machine is now in the Smithsonian. He defined a perceptron as a network of S, your sources, your accumulators, and R is your results, with variable interconnection to a matrix, depending on a sequence of past activity and states of the network. So that's what he was thinking of when he was defining it. We kind of use the same definition today. Here's a figure from his original document, having your input, your weights coming in, multiplying things. Okay. Universal cross-coupled is a big thing that comes in with the network. Rather than just going one way, we're going to cross things from one to the next. Training, there's a control unit. Error correction based on what things were somewhat manually labeled as wrong. And through there, the weights were controlled. And this is talking about a control system similar to what you might learn about if you were to take our control systems class. Just very, very much, you look at errors and you minimize errors, and errors feedback weights, and weights update things. This is 1958, 1961. We're talking very basic ideas, not today's ideas. But if we didn't have these ideas, we would not have gotten where we're at today. So he said that he thinks that there exists some universal perception, some universal thing which could do this learning element, And he felt it had to have 3 layers minimum. But again, think of how complicated things were then. 3 layers was an awful lot. He had a bunch of mathematics going through things. He felt that there was a possibility that things could come in and lead to convergence of a solution of good weights. And a lot of it's through linear algebra. And a lot of it depended on that linear separability idea. I'm hoping is coming there, which today we think about as finding our solution zone. So 4 layers, perceptron, similar idea. I'm going to show you old slides. And now the more interesting ones. Let's do this thing. Whatever. So with Mark 1, 400 units. 500 accumulators, 8 results. Here's pictures of this physical thing. Again, this is in the Smithsonian, not always on display, but in their warehouse. They got big warehouses there. Pretty fascinating. Really, really large, room size. And that was the second machine that they put together was called Tobermory. Which had even more units, it was even bigger. That's C there for Cornell University. Tobermory had built on the same idea, but made it even bigger. Physical room, control room, physical soundproof control room. People can stand in here. Nothing big. One of the training mechanisms we use, we still use it a lot today, is back propagation. You'll learn this in the coming weeks. And we don't really think that he was thinking about this when he was doing his design. Okay. That came out after his time. A lot of the money off of naval research money went to machine construction. And they did a lot of work on general computers and taking that particular big computer on their own working on them. But that's also been the way that a lot of research has happened in general. Somebody puts money in, you build something, somebody else tries it other ways, and eventually you kind of figure out what works, what doesn't work, and you pick the best and move on, always improving from the next. So it's able to do corrections, able to converge, has led to a lot of other things afterwards. We now know a lot more, but his stuff really has led into a lot of these decisions. And again, I display this because George is my advisor, and so I've got access to this stuff. And actually, what George said that he spent a lot of time working on, and he's kind of glad that these results didn't happen, is taking physical neurons from mice and seeing whether they could be programmed. He worked with. And he said he's really happy those experiments did not work. And we did not go that way with trying to build physical biological brains out of mice neurons. But that's what he spent part of his doctoral work doing. But some of the other stuff was built on there later on. And there. Lots of little pictures. I think it's fun to see the history. So 1958, Frank Rosenblatt made some major steps forward based on biology, building and electronics. Building on the idea of the linear discriminant, which is where I started today's lecture, based on what you had with linear discriminant last week. The problem with linear discriminants is that they produce linear decision boundaries. And one of the things they thought about as a really big problem was the XOR problem, famous XOR problem. If we take inputs for feature 1, inputs for feature 2, so this is our space, feature space, feature 1, feature 2, and we say that they are the binary values 0 and 1, exclusive OR of 0 and 0, exclusive OR of 0 and 1, exclusive OR of 0 and 1, or 1 and 0, exclusive OR of 1 and 1. You cannot, this is not linearly separable. You cannot draw a straight line and separate this. So all those great linear discriminant functions will not work on a somewhat simple problem. You can build an XOR gate with stuff from digital logic, from your digital systems class. And yet still, the techniques from pattern recognition, which depend on linear separable data, cannot work on a simple problem. So a lot of papers focus on how can we build something that can solve this. Because we can't do this nonlinear, simple nonlinear problem. How do we even solve a complicated problem? Because they're trying to figure out whatever. So always try the simple things first. And because it couldn't solve this nonlinear, very simple problem, we said we really wanted to try something else. The single layer perceptron could not solve XOR. And if you read anything historical, they're always backing up to this point. Can you do XOR? Okay. And so therefore, because his perceptron, when you take a single one, cannot do it because it's not linearly separable, a lot of the ideas got dropped for about 20 years. And that's very common in research. You've got an idea, but you come up against a problem, it doesn't work, you can't solve it. Or you can't solve it how you wanted to solve it. And then the community says, well, it just doesn't work. It was a great idea, it was fun, it just didn't work. About the same time that Rosenblatt was working, Woodrow and Hoff were working and developing two other neural networks called the Adeline and the Madeline. And those there are just, again, looking to predict binary values, looking at binary values, the same general way as the perceptron. And then Minsky and Papert revived the perceptron idea and probably coined the name a little bit more, making it more popular at the end of the 60s. And they also put a nail in the coffin by saying, well, this is what perceptrons cannot do. They proved it cannot do this, it cannot do this, it cannot do this. And everybody else said, geez, wow, you're right, let's not do this. Until several years later, some grad student, having been reading carefully, came up and said, well, geez, let me see if this will work. Oh, well, what if we do it this way instead? You take that, what if we do it this way instead and change how all the old timers have been doing it? And lo and behold, the new way works. And it's not that the old way was bad, it's that you needed to add something else to it. You needed to look at it a little bit differently. But Minsky and Papert pretty much put the squash on neural networks in '69 by proving what this mathematical perceptron with linear decision boundaries could and could not do, because so many things were there in the could not do category. Everybody said, well, this is not any useful. Why, the funding agency said, why are we going to put money into something that's not going to do these things? And if faculty don't get funding for it, they're not going to do it. And so a lot of it is dropped. So I want to define several different types of neurons. Let you see the difference for where we're at. In the top left is the adaptive linear combiner. You take the inputs, you scale them by a weight, and you accumulate. And then you pass it through a linear function, which means do nothing. Don't change anything. And so that's purely linear coming out. It's adaptive linear combiner. Your output is a continuous value from -infinity to +infinity. But the adaptive part means those weights can change. The Adeline has the same input, but the output, instead of being linear, is a threshold. Zeros and ones come out, -1s, +1s, depending exactly how you want to define it. Doesn't really matter. The perceptron, when revised, had that same starting point, but now has a non-linear output. That nonlinear output could become the key to what makes neural networks successful. So they took that perceptron, and when they added in that nonlinear output, that's when things are going to start working. And a threshold logic unit is the same thing, but your inputs are all binary. And then you threshold it on the output. And so therefore you can create different logic units by just changing the weights. You can kind of think of that kind of as a prehistoric FPGA. It's the logical devices where you can reconfigure them. What I want you to see is that these all look kind of similar to each other. They're built on the same idea. The biggest difference is what happens after you accumulate. And the key comes in putting a nonlinearity. Because we already talked how XOR is not linearly separable. And lots of other problems are not linearly separable.
Are we going to talk about this nonlinearity output later?
We're going to talk about it. Okay. So when you have things that are not linearly separable, we got to do something else about it. We talked last class about SVMs, where they just simply expand your feature space. But instead of having X, have X and X squared, and X cubed, and X times Y. So to get around it that way. And you can always do that. But that then adds to your number of inputs, that adds to your number of weights. And at a certain point, complicated is just not good. But these ideas are all related. And they're all built on the same starting point. Taking a bunch of inputs, scaling each by a weight. And if you choose the right weights, you get something useful out. Then those scale weights get added and then pass through some sort of function, whether it's linear, threshold, or nonlinear, something. And the TLUs are a little bit different because the inputs are binary, but otherwise they're the same. So we're working our way up towards modern neural networks. Neural networks are going to have inputs. Those inputs are your features. M00, U20, U11, etc. You should be very friendly with them right now. Okay. They're going to have outputs. We got to figure out what we're going to have for outputs. The top one is a so-called one-shot output. So you've got how many classes in your project?
10.
10. So we'll have 10 outputs. One output is to say, hey, I'm an A. One output says, hey, I'm a C. One output is, hey, I'm an E, all the way down to Z. And you want it to only fire one for whichever one is the true one. That's just one shot output. You can have an output which is analog, 1, 2, 3, 4. So an A is a 1, C is a 2, and E is a 3, etc. You can do that. You can do a mixture between them by saying we're going to represent an A as a 0, 0, and a C as a 0, 1. So having two outputs, which are binary. We need to have 3 for 10, 4 for 10. But we can do that. So you're going to have outputs, and there's options out there for what you choose your output to be. Most commonly, the first one is used, but you have options. I want you to know that you have options. Okay. Just as everybody's always done it doesn't mean you can't change it. If you're going to come up with the next great idea, maybe you're going to change it. Then there's going to be in all neural networks some sort of internal network structure. Who's connected to whom? And then what's going on in the nodes? Everything has your values times the weight in an accumulator, but these options here, all of this are included in your node. What you put for this output linearity or nonlinearity function is your other characteristics of your node. And then your training method, how do you choose those weights? There's multiple ways of choosing them. Several are based on gradient descent. You will implement a gradient descent-based method in project 3. And then you've got your output, and you need to assess, is it working? How do you decide, is it working? You've got options there for just raw error rate. And you've got options for, okay, I wanted to have 1000 as the first output, but I got 0.9, 0.1, 0.1, 0.1. And so you can take a difference between those totals, and you can look at an analog Euclidean distance from where you are from what your goal is. So there's lots of different ways for assessing it and saying, are you good or not? Because getting your network to give you a 0.9, 0.1, 0.1, 0.1 is a lot different than if it gave you a 0.6, 0.4, 0.4, 0.4. You're a lot closer to, I might not make it next time. You really want to consider, are you just barely passing with a C minus? Or are you passing with an A? Both are passing, but they're not the same. So as we design our networks, these are things which we need to consider and build into our design. All of them will have these as issues. Remington.
The performance of systems, you also have to worry about like local maximum and all that.
That's built into the training method. You perform whether once you pass those minimums, did you get stuck in the minimum or did you get over the minimum down to the pure minimum is determined in how well your output is performing. So it's not specifically saying, are you in a local minimum? But if you're in a local minimum, your performance is going to be lower. Or maybe even be terrible. Okay. So there's lots of different types of networks, looking at the connectivity, how are we going to arrange that connectivity? How are we doing the layers? Are we just going forward and backwards? We got all the little neuron pieces floating around. And we define a couple of different ways. Feed forward said nodes are only going to be connected between adjacent layers. So we're going to come up with a number of different layers. Number of different layers. And we can say that we're only going to connect between adjacent layers, and we're not going to jump to the next one. Between these two layers, and not jump to the next. And we're only going to go forward. But the output of this is not going to feed back in. Feed forward. And that's what's most common. And we can think of this as taking a whole bunch of Rosenblatt's outputs and putting them one after the other. Cross-coupled, you can feed forward and you have connections to other ones in your same layer. So we can have talking within the layer. Back coupled, that's where you're going to feed the output back. to the previous layer. And fully connected is included in each of the ones above, meaning that every node here is going to be connected to every other node in the next layer. I'll show this in the next diagram. Everything within the one layer is the next layer. So we're going to say that every input is going to be connected to every accumulator leading to an output. And I2 is going to be connected to everyone. I is connected to everyone. ID. D is the number of features. C is the number of classes. And if it is fully connected, how many weights are there going to be?
C times D.
C times D. So we're going to consider your project. How many features do you have? How many output, how many classes do you have?
10.
How many weights would you have if you had just a single layer? 80. Okay, simple math. We're going to have our sources, which are inputs, our weights, and our outputs. We're going to take our sources, each individual input, scale it by a weight. We're going to accumulate and form an output. So each input is scaled by a weight to form an output. That's how you get here. I1 times W1, 1, I2 times W1, 2, down to ID times W1D will form output 1. And we can continue that down till we get over here. So this was for output 1. I1 times WC1 will give us this, plus I2 times WC2, down to ID times WCD to give us our last one. And there's a whole bunch in between. We're going to have 10 of these equations for linear data. This is linear. So we can represent those weights as a matrix and those inputs as a matrix. The product of those two matrices, those two vectors, will be your output. Right? So if I give you just one data point, we're going to have C by D weights. You just said that. 8 by 10 weights. D by 1, 8 inputs. Take your first A row. Take a train.dat. Take that first thing from your train.dat. Those 8 values here. That's this guy right here. And when we use whatever weights we have, we're going to come up with a 10 by 1 output for A, for the first A. But you've got more than just one data point. For your data set, how many data points do you have?
100 or 200.
100 in the training. Start with the training. So rather than just doing this once for one input, we're going to do the same network, same weights, but after showing it A1 and getting 10 outputs, we'll show it A2 and get 10 more outputs. Then we'll show it A3 and get 10 more outputs. Until we finally work our way through all the A's, the C's, the E's, down to the z's, and finally at the end, the last z, z10, m00, mu20, mu11, going to give us outputs for the last z. We're hoping that these outputs for all the a's will be a 1 here and zeros here. Hoping. We're hoping that for the c's, we get a 0, a 1, and a whole bunch more zeros. If we get good weights. And we're hoping that for the z's, z, zeta, then we're going to get a whole bunch of zeros and a single 1. Right? Ready with us? So this is the equation for one data point. We've got n data points. We have 100 data points. We're going to still have those equations. But now, if we take what those equations are for A, C, 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 Z, 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 these inputs, we can stack them next to each other. We have these equations, D equations, n times.
So the ends are the plus one.
Yeah. These are just dimensions of your vector, weight vector, your source vector, and your output vector. Weights are a C by D matrix. We decided that there were 8 by 10 weights in here. 8 features, 10 output, 8 by 10 weights in here. C is 10, D is 8. This is really important that you get this.
So now we use X is the source.
Source, this is your input.
What do we put in the weight?
Later, we're going to figure out how to determine the weight. So I'm about to say one aspect of that. But if you guys can't figure out this math as we're at, determining the weights isn't going to get you any good.
Right, we can't use anything.
Where some students lose it, so I'm going to try and bring as many of you along as I can. And I'm hoping that those of you who might lose will ask me sooner than later. So if I'm about to lose any of you, make sure you ask me soon. Don't just let this sit until you're the product due tomorrow night. Okay? So when I consider the fact you've got 100 data points in your train file, these 10 equations turn into 10 by 100 equations.
So just to make sure C is the number of classes.
C is the number of classes, which is 10 for you.
And then D is the number of features.
D is the number of features, which is 8 for you.
Maybe you're going to get to this, but do you not want to do the data points sequentially so that you can feed back to your weights after each point?
Hold on that thought.
Okay.
That's not applicable at the moment.
Okay.
But it's a good thought. It is applicable later. It's just not right now.
Okay.
So just time out.
Sure.
We'll come back to that. Okay. So if we know our inputs, we know our desired outputs, and we don't have any nonlinearities here, in theory, we can just solve the set of matrices. Is that concept sort of clear? So we can write this as a matrix problem. Do a least squares inverse, pseudo inverse, and you can solve, and you can determine those 80 weights. Because we've got 100 equations, times 8, we got all those extra equations. We got plenty of data to do a good pseudo inverse. Even though we've got 80 weights, that's a lot of weights, a lot of unknowns. A really big W matrix. 8 by 10, that's big. You do not want to be doing this by hand, folks. It's big. Even your calculator will try. But we can find those 80 weights if we consider our n data points. And expand what we started with at the top from D equations to n by D equations. From 8 to 800. And then you've all had pseudo inverses to solve an overconstrained problem, a well-defined problem. And so you could solve that for your 80 unknowns. Okay. Come back to that. The problem starts coming with the fact that that requires a linear decision boundary. So solving linear equations. For those of you who have not taken linear algebra, which at Boise State is ECE556-20220303, it's a great useful course. Okay. But it's a lot of just linear algebra, and you typically do linear. And if we're talking about putting multiple layers together into a deeper neural network, we're nowhere near deep learning yet. I know we'll get to that in a couple weeks. We can add more weights, which could do something, but it's all going to merge into one common problem. Even adding another set of weights. Because we would have here one linear equation, and then here we would have a similar set of equations for the next set of weights. And if there's nothing between the two, if it just comes out and is linear, we can then take these and adding another layer isn't going to do you any good. You're going to have a bigger weight matrix. It's still going to be linear. So adding another layer, if we don't do anything to the output here, we think in this situation, not doing anything to the output, isn't going to do you any good because we can just put two sets together and those two would just merge and be equivalent to what we started with. Still linear. Bigger, but linear. The power came, and this problem is a lot of what Minsky and Papert first discovered. They said, yeah, you can put lots of them together, it doesn't do any good. Because it's still linear, still can't do it. So then people said, okay, let's add a nonlinearity after the accumulator. Add a nonlinearity after the accumulator. And then it no longer resolves to this because we now have a nonlinear function of those outputs. And so it's no longer just linear. We add a nonlinear function called f. This is called an activation function. It's a nonlinear function. Remington,
How do you go about choosing a activation function?
we'll get to that.
The reason why we want to have the nonlinearity is to solve more complicated problems.
The reason we want to add that nonlinearity is to solve more complicated problems. Something with a non-linear decision boundary. If things are linearly separable, great. But without that nonlinearity, it's going to have to be linearly separable in order for the initial method to work. Adding that activation function F brings it from a linear decision boundary to a nonlinear decision boundary. And now we can do more. Think back to homework 3, 2 dimensions, linear versus nonlinear decision boundaries in that 2-dimensional classification GUI with the red and blue. The different shape boundaries. You can do more things, so dots can be different places on the other side of the decision boundary. You make different things. And we're not limited to just quadratic either. By putting in that activation function, it does not need to be quadratic boundaries. Something nonlinear. And something nonlinear can handle that XOR problem. And more important than the XOR problem, it can handle lots and lots of other problems that are nonlinear. Because they exist more often than not. Now, historically, we've started with the linear ones. Always do things easy first. Always solve the easy problems first. If you get a test, do the easy problems first. At least get points for them. Okay. But some places have it when you do the hard problems. And as we evolve over time, we get to harder and harder problems. So they started with a lot of methods which are linear. K&N is not linear. Bayes is not linear. Does not have to be linear. It has to be quadratic in n dimensions, d dimensions. And here we can get into other nonlinear decision boundaries by adding this nonlinear activation function between our layers. So remember, we've got our inputs coming in, our weights, they've accumulated. Something comes in, we call that accumulation a net, sort of like a net sum if you're in finance. Your net value, net sum. And then we're going to take some activation function of that. Getting an output, we'll call it Z at the moment. So that. This guy right here is just linear ops. We can do the same thing with a 3-layer network. But again, we need to have those nonlinear activation functions. Otherwise, it just collapses. We just keep working our way forward. There is conflicting terminology in the field about how we count the number of layers. How many sets of weights do you see?
3.
3. Some people call it a 3-layer network. How many hidden nodes are there?
2.
2. 2 layers of hidden nodes. So there's some conflicting terminology. Listen carefully to how people describe things. Okay. 1 hidden layer, 2 hidden layers, a 2-layer network, a 1-layer network, a 3-layer network. Listen carefully to how people describe them because there's a mismatch in the numbers just because of what are you talking about? So just be aware of that. Okay. That's your project too. You're not done yet. So if you need more time, get it done. For those of you who have nothing better to do this weekend, you can start coding this general network. If, and this is what homework 5 is going to be, I'm going to give you values for the weights for your layers. If I give you an input, like the first A, mu0, 0, mu2, 0, mu1, 1, etc. What will the output be if I also gave you that function? What do you just leave it arbitrary? How would you code to take those 8 input values and get 10 output values? If I gave you the weight value and I gave you that function. That's where you should be kind of thinking. That's what I want you guys to be coding next. So if you're done with project 2 and you need something to do this weekend to keep you off the streets. Okay, that's what you can code. I'll put that into writing soon. If you're not done with the project, get it done.